Okay, we're talking about orbits. In order to do an orbit, we kind of have to go to one of Newton's thought experiments, at least to understand it. What he said was if you had a mountain on the planet, that's a wonderful planet, wonderful mountain, and he said if you put a cannonball on top of it, and fired a cannonball, it would do this. Familiar parabolic trajectory, 1/2 AT squared, all that stuff. If you add more power to it, you'd have that. If you add more power to it, you'd have that. And if you added enough power to it, it would simply go into orbit. So key thing to think about is that's what we're talking about with orbit. Now, let's take a look at it when it's out in orbit and watch what happens. If I have this International Space Station, if I draw the International Space Station here, it's floating up on top of Earth, that's a wonderful picture. And if I was to draw a free body diagram, remember, trust the free body diagrams. If I draw it, and down here someplace I have Earth, what's going to happen now is I have mg acting down. You can also call that fg if you want. Either one, you can do that. And the key thing is it's moving like that. It's moving in a circle. There's no other forces. There's no friction. There's no normal force because it's not in contact with anything. That's the only force that's there. So when I go to Newton's second law, the sum of the forces equals mass times A. Hey, circles. As soon as I know circles, I know that this is mv squared over r. There's a centripetal force. And the sum of the forces is actually m times g. So in this case, gravity actually supplies this centripetal force. Remember, centripetal force always comes from something else. In this case, it's gravity that does it. If I go to this, then what's going to happen is I can solve for v, and I get v squared. Hey, my m's cancel out. V squared is equal to r times g, so v is equal to the square root of r times g. So that's kind of neat, and that will allow you to play around with a little bit to find the speed if you know the radius and you know g at that location. Now let's take a look at g at that location for the space shuttle. The space station. So it's at an altitude of 380 kilometers on average above the surface of the Earth. And what I want to do is I want to calculate g at that height. Now, go back to this equation, F is equal to g m1 m2 over r squared. And remember, F is also equal to m times g is equal to g m1 m2 over r squared. Get rid of one of the m's. I get g is equal to big G, the mass of the Earth, which is the other thing involved, divided by the radius squared. Well, we know the mass of the Earth, 6 times 10 to the 24th kilograms. We know the distance, the radius of the Earth is 6.4 times 10 to the 6th meters. And what I'm going to add is 380 kilometers, 380,000 meters to that. And that's going to be added to the 6.4 times 10 to the 6th meters. When you plug that in, you get g is equal to 8.7 meters per second squared on the International Space Station. It's only 11% less. The astronauts are not weightless. The difference is, the reason they feel weightless is because they're falling. But so is the space shuttle. So they're both falling. Since they're both falling, they don't press on each other. So therefore, they don't feel anything. Now, Let's go one step further with that, with planets. And something hopefully neat will come out of this. If I'm going to say that FG is equal to FC, what I want to do now is take into account and show you what happens with planets. Now, so this again is going to be big G M1 M2 over R squared. This is equal to M times V squared over R squared. Get rid of one of the M's again and get rid of it. Okay. Now we play with it. I also can get rid of one of the R's if you look at it, because I have an R and an R squared, so I can multiply through by R, which gets rid of one of those. Let's rewrite that. I get V squared equals big G times the mass of the planet divided by the radius. And again, that's not the radius of the individual planet. That's the radius from the sun to that planet. So then I get V is equal to the square root of big G times the mass of the planet divided by the distance to the planet. Again, what this shows is the fact that the farther you, as the radius goes up, in other words, as you get farther away from the sun, what happens to the speed? V is going to go down. So therefore, Mercury is the fastest. And, well, I love Pluto. Pluto, slowest. Okay, we'll play with this a little bit more in class.